The title of this presentation is Asymptotic Approximation of 81 Poisson Brackets for Triangular Ice. So to begin with the presentation overview, we'll be describing some general characteristics and background more briefly in this part of the series to establish further how we can provide a little bit more detail from the notions that we mentioned previously from the set of relations with the Poisson bracket that were obtained for triangular ice. So as we've been mentioning throughout several different parts of the series, we're looking at different connections with statistical mechanics, whether it relates to crossing probabilities or RSW, the localization of the height function for the six vertex model or other vertex models. And in particular, in the case of triangular ice, we have really been looking at integrability from the quantum inverse scattering method. And we've been making use of algebraic notions that were introduced from integer valued or set valued flagged tableau, which give expressions for lasso and several variants of the double Grothendieck polynomial. And we also discuss how solutions to the Yang-Baxter equation are important for the colored R matrix, as well as the fact that these solutions to YBE also appear as properties of the universal R matrix, and how that has several algebraic and combinatorial aspects, and how that can also be related to making a connection or a correspondence between the colored partition function, as well as looking at different assumptions on the quantum inverse scattering type method from these objects that we construct much earlier in the arguments before we start any computations with the Poisson bracket or any computations with regards to the L operators, whether the L operator is two-dimensional or three-dimensional. And now I'm going to also provide a quick flashback as we're still recapping things from an overview of the third presentation, in which we provided more details of the three-dimensional quantum inverse scattering type approach. And we added on to general descriptions provided in earlier parts of the series. And at that point of the series in the previous presentation, we were providing information and addressing following questions for making further connections between the two and three-dimensional approaches, which is related to the fact like how we had been mentioning and further building on in the previous presentation in the series when we were discussing how one can obtain a set of 81 relations and how that relates to some generic three-dimensional representation of the transfer matrix that we're going to hope to study further entry-wise for each of the 9 entries from the multiplication and the structure of the L operators, like how we saw that there is a very strong dependency of a sign of two eta factors, as well as the poly bases in the two-dimensional L operator. So for the three-dimensional L operator, this was also drawing our attention to, as is said in the second bullet point, how is the three-dimensional transfer matrix defined? And in the third bullet point, relatedly, how is the three-dimensional quantum monodromy matrix defined? And this is all related to the fact that it brings our attention to how do computations with the L operator expressed in the Pauli matrix from the two-dimensional setting transfer, or whether there's still any useful information about or general information about the Poisson structure in two-dimensional case and how that relates to the Poisson structure in three-dimensional case, which we're able to look at in terms of the sets of relations from the Poisson bracket and how that relates to different entries of the three-dimensional or two-dimensional transfer matrices. And as we had also mentioned, additionally, we further described how algebraic connections from the three-dimensional L operator along the lines of those mentioned in the previous part of the series relate to staggering and inhomogeneities in vertex models. So there's different ways in which we can either introduce staggering or inhomogeneities to a certain group of vertices which lie within either Z2 or Z3. Like, a lot of models, they've looked at staggering when you only introduce some effect along the even vertices. So you basically fix like some counting system, like, or some ordering like lexicographic order or some other type of standard ordering for all the vertices that are included in finite volume. And then you can introduce different types of staggering depending upon like which vertex of the lattice you're occupying in the configuration. So this very much relates to how we can look at some more basic vertex model that doesn't have any of these types of assumptions on either staggering or inhomogeneities, and then how we can look at different types of boundary conditions, and then whether there will be any type of information that we can still extract, or whether there will be any type of change of behavior or change of properties of the 6 vertex model or even 20 vertex model, like we've been introducing with the diagram and the figures from the DiFrancesco reference. And as we had mentioned, there are several other references for discussion conditions for exact integrability or exact solvability and integrability that are not mentioned in the previous talks of the series. And like we had mentioned, we can look at several different aspects and connections with the algebraic beta ansatz and some inverse scattering approach. So it's just maybe a little bit of a different set of assumptions that are placed on the argument between rather than those that are included in the quantum inverse scattering approach, but still it's a scattering approach nevertheless, so it has still many types of similarities. And there is even other seminal work from Fadив in which he talks about other aspects of the algebraic beta ansatz and how those conditions relate to integrability. So we can see very much how all of the presentations and themes that we've been bringing up throughout the series, they're kind of coming together and they're offering a rich type of set of connections between different areas, and how really you can start mostly from a discrete probability perspective, but from these types of discrete settings, it's very helpful because you can look at different ways to encode these representations for how some types of interactions occur over 2 or 3 dimensions, and how the 3 dimensional case, undoubtedly, while it's more complicated, it still can give very many connections from the information that we hope to establish or hope to show from an integrability condition in a 2 dimensional case. And so, in the previous parts of the series, we discussed from several perspectives the L operators of the type below, which hold up to Dynkin automorphism. So, there's a different type of contribution from these L operators, whether it be the mapping into the unital associative algebra, which is the complex valued function xi, and this is responsible for staggering and also in homogeneities that we can introduce at different sites of the lattice of over 3 dimensions, over which, or sorry, the triangular lattice, sorry, not 3 dimensional, just a triangular lattice that we would like to study further. And we had talked about how the expansions of the 2 dimensional transfer matrix in the large N limit are obtained from products of L operators, which is some general aspect of structure and structure of the computations that we have to perform in 2 and 3 dimensions that come into play. And this is given by the fact that we can introduce, as we had mentioned in the previous presentation in the series, a reformulation of the L operator, which allows us to be able to perform and put ourselves within the framework of previous computations that we carried out in 2 dimensions, and how it relates to this 16 set of relations. And we can look to define triangular ice. And we can look to define triangular ice by looking at different configurations that we can obtain for another vertex model that's a 3 dimensional 6 vertex model over the triangular lattice, in which we can group the configurations in groups of 10 for 20 total configurations that are given in the sample space. And this is related to the fact that different configurations that appear in the sample space, which are pretty much complementary to each other, can be obtained, which have the same weight. So we can group these 10 configurations in the top row with the 10 configurations in the bottom row, which can then receive weights like we had defined earlier in the previous presentation from the DiFrancesco reference, omega naught up to omega 6. But to further describe where additional computations with the Poisson bracket arise, we introduce the following representation of the 3 dimensional transfer matrix. So we can just say that for convenience, we can denote lambda, which is a parameter that's introduced in the definition of the 3 dimensional transfer matrix, as a homogenization parameter, in the sense that we can take 2 spectral parameters and converge them to a single parameter lambda. And then for the other parameters that we have, which enter as dependencies on the 3 dimensional transfer matrix, we also have M and N, which represent 2 degrees of freedom that we're taking the infinite volume limit of. as well as the fact that corresponding to M and N, there are collections of other spectral parameters, V sub I and U sub J. So we're looking to take the limit as N goes to infinity and M goes to positive infinity of this three-dimensional transfer matrix. And as we had mentioned earlier in the last presentation of the series, there's a set of 81 relations that arise instead of 16 that's given for the two-dimensional case. But still, there are many just similar characteristics and properties of the Poisson structure in two-dimensional case and how one obtains the complete set of relations that can be extended in a straightforward manner to three dimensions. And from the three-dimensional large N limit, the entries of the transfer matrix when forming the system of Poisson brackets of entries of the transfer matrix takes the following form. As we show here through these columns A, B, C, D, E, F, and G, H, I, we have a three-dimensional generic representation of the transfer matrix. And that's relating to the set of 81 relations, which are in the background, which take some computations and approximations in the asymptotic large N limit with the Poisson bracket, because from relations 19 through 27 within the set of the entire 81 relations, we can see that when we hold one of the entries of the generic representation of the three-dimensional transfer matrix C of U, this fixes the first argument of all these Poisson brackets which appear with C of U within the set of 81 relations, but also then we can just interpolate between all of the remaining entries of the three-dimensional generic representation of another transfer matrix that has parameters U prime in all of the entries instead of U, and that will constitute all of the remaining terms for the second argument of the Poisson bracket. And once we're able to make these types of connections, even though some types of terms or computations for multiplying L operators, it may be a little intimidating at first, we can just push through with a couple of brute force calculations to obtain and infer some general type of structure of the individual elements are given in this three-dimensional generic representation. And then very much we're in kind of like a two-dimensional case, because even though we started with triangular ice, we just encounter some similar sets of relations with the Poisson bracket from the set of the 81 relations, but we just have additional terms from the new 3x3 dimensional generic representation that we're using just as we're carrying out the multiplication of L operators and determining what is a generalized form of the terms that result from these computations. And like we had mentioned, the reformulation of the three-dimensional L operator is given by the fact that we're just looking to enforce a differential operator at each side of the triangular lattice that we're measuring the three-dimensional interactions of with triangular ice. And we can just fix the basis of the triangular lattice of E sub k minus 1, E sub k, and E sub k plus 1. And then we can just factor in this type of reformulation by adding in an additional index so that we can look at taking various limits for J and K subsequences of this of the product of these L operators and taking the trace, which can be used to approximate some asymptotic properties of the transfer matrix. And so for approximations of the three-dimensional transfer matrix as given by an expression of a matrix product of this form, we closed out the last presentation of the series then by talking about how we can turn to a system of Poisson brackets to approximate the large N limit and how that's related to the two-dimensional system of Poisson brackets. And so what the concluding remarks for the three-dimensional case were that we were discussing more details of the three-dimensional quantum inverse scattering type approach, and we were talking about how to define and further make sense of the Poisson bracket and how the dependencies from the entries of the transfer matrix with the Poisson bracket help us gain information about the three-dimensional quantum monodromy matrix. And so we're going to be defining the three-dimensional quantum monodromy matrix in these slides, which we didn't introduce last time. And then this will allow us to just further discuss some other aspects of the computation with the L operator and how that comes into play with the Poisson bracket. And we're going to emphasize again that the 81 relations appearing in computations in three dimensions with the QISM type approach in comparison to the 16 relations appearing in the computations in two dimensions. So we're still going to be able to use very similar aspects and properties of the Poisson bracket. Just we're going to have to look at different types of combinations of interactions, and there are more combinations for interactions to occur in three dimensions rather than in two. And so several aspects of the L operator can be phrased in terms of the set of all linear combinations of three one-dimensional subspaces. So we're going to look to vary J and K over the naturals because we want to take a larger weak infinite volume limit to approximate the entire triangular lattice in their interactions that may occur from different configurations and patterns of configurations that can arise in the 20 vertex model. And from this base setting that we're looking at for the 20 vertex model, we can have script B sub 1, script B sub 2, and script B sub 3, and take the set of all linear combinations, which will correspond to some representation that has the same dimension as the product of the L operators from the three-dimensional representation of the families of L operators that we had introduced, which hold up to Dynkin automorphism. And the infinite volume limit of the transfer matrix is proportional to the infinite volume limit of the quantum monodromy matrix. And this is just given by the fact that we can still take a limit as n and m tend to positive infinity. But the thing is that we need to perform some additional computations or insert some additional dependencies from the quantum or from the three-dimensional transfer matrix to obtain the three-dimensional quantum monodromy matrix. So that is just, that can just convince ourselves that allow us to feel convinced that their infinite volume limits should be proportional. And the notation that we adopted, as we mentioned last time, is that the three-dimensional limit of the transfer matrix, either at plus or minus of x of lambda, is given by just the limit as y tends to positive infinity of the finite volume approximation for the three-dimensional transfer matrix multiplied by this E quantity, which I'd mentioned it's introduced in the preprint, but it's very much related to the two-dimensional quantity, which is defined in is related to a tensor product. And an infinite volume representation of the transfer matrix takes the following form. So we're just still taking this matrix product, but we're taking the trace of it, and then we're taking the limit as it goes to infinity. And this is just a three-dimensional transfer matrix. And this is the types of properties that we would like to study, which very much relates to, as we have been mentioning, the same direction of research that appears from the characteristics of the two-dimensional transfer matrix from the Pauli bases. And the infinite volume and homogenization limits are defined also in the preprint, given by the fact that we can take lambda sub I or any other spectral parameters to go to lambda, as well as still taking the limit as m goes to positive infinity, as well as the limit as n goes to positive infinity, and then looking at the the boldface of T, which is denoting the three-dimensional transfer matrix, which is just amounting to a trace over each one of the degrees of freedom, m and n, that we're taking the infinite volume limit over, as well as the fact that we have other spectral parameter dependencies. So this is just giving some of the, pretty much most of the parameters that are entering into the dependency of the transfer matrix in the infinite volume limit. And in two dimensions, the quantum monodromy matrix takes the following form, in which, because we introduce the two external parameters or external fields H and V, for the definition of the two-dimensional quantum monodromy matrix, we have, that the position U comes into play, as well as the spectral parameters B sub K in the two external fields H and V, which is given as a tensor product in which the pre-image space and the image space are given by the same space, because we're taking the tensor product of C squared, the two-dimensional complex space, tensor product with this same space raised to the tensor product of n into itself, which is given by a diagonal matrix, a 2x2-dimensional diagonal matrix with just E exponential of 2 times one of the external fields multiplied by the R matrices, and we're taking this product over I, where again we've been making use of the two-dimensional the 4x4 two-dimensional R matrix, which is expressed in terms of entries that are given by the weights of the 6-vertex model parameterized in the two external fields H and V. And we very much want to make further use of the computations that we were talking about in the previous presentation of this series. And this is given by the fact that we can look at all the terms that we have as some type of dictionary. It's a dictionary because we can look at various linear combinations or products of these terms which appear, which are either dependent upon Q parameters raised to some differential operator, or you can look at, as we give in the third line, some contribution from the the complex valued mapping into the unital associative algebra, or we can also have other types of parameters which are related to Q. Uh, so so this allows us to try to make some sense of these different contributions and how they appear in the L operator and products of L operators, which will ultimately relate to different terms which enter within the set of 81 relations from the Poisson structure. And the three-dimensional generic representation of the I or of the K, sorry, the K limit of the three-dimensional transfer matrix, it can be expressed, oh yeah, in terms of an I limit because we introduced these notations for I just to denote 1 sub I, 2 sub I, and 3 sub I, which is indicating the product of the L operator along one coordinate while we're holding the other coordinate fixed. And to take the infinite volume limit, we have to look at the limit as big N tends to positive infinity, where big N appears as the upper index of the product. And this product of matrices is proportional to a 3 by 3 dimensional representation of the product of L operators for the infinite volume approximation of the three-dimensional transfer matrix and the U prime parameter. And in turn, this 3 by 3 dimensional representation is proportional to the Poisson bracket, the tensor product of the Poisson bracket of two 3 by 3 dimensional representations, which is exactly relating to the Poisson bracket that is a degeneration into the 81 Poisson brackets, which appear from the set of relations for the quantum inverse scattering type approach in 3 dimensions. So this is making it very clear and spelling out how all of the components that we have been talking about throughout different parts of this series are coming together in the sense that we're describing and we've introduced the three-dimensional objects. We've looked at how when you go up to 3 dimensions, some rigidity or some very specific characteristics of the two-dimensional setting don't transfer over. And in describing those types of differences from the 2 and 3 dimensional approach, we're able to show how it just results in a more complicated notion of Poisson structure in 3 dimensions because it's just relating to a broader set of relations and possible combinations of interactions that can occur for the triangular ice in the 20 vertex model over the triangular lattice. And the figure with spectral parameter labeling can be shown in which it's just a figure that I adopt from the logarithmic delocalization paper because it's showing that from a figure that I reproduced from another preprint under slope boundary conditions, which is a very specific case of boundary conditions in which with positive probability, some portions or some connected components or regions of the finite volume will be of the same vertex, which induces some freezing of the height function. We can decorate and place spectral parameters along different parts of the finite volume. Like I placed a lambda factor everywhere you can have an edge that's lying along the boundary that would contribute to some staggering or some other aspects of the vertex models that weren't discussed in that setting. So even though it's very much, this is a type of configuration that we were looking at and discussing for Russell-Seymour-Welsh and crossing probabilities, still the Russell-Seymour-Welsh, it gives a good idea or a good type of intuition about the types of configurations that you could sample from a 6 vertex sample space, either under different boundary conditions or in homogeneities or staggering, and how we can still try to make some connection between these seemingly disparate areas. And the three-dimensional quantum monodromy matrix, as we had referred to it, can be defined as the fact that it's some expression which is a map given by T three-dimensional A of B, which is dependent upon the U position as well as two spectral parameters. And in this definition, in this definition of the mapping, we can just sidestep for the time being, not having to introduce the two external fields H and B, although someone can trivially do it, which I also have provided it right under this definition in the preprint that's coming up. But the pre-image and the image space of the mapping, as in the two-dimensional case, also in the three-dimensional case, are the same, and it's just given by a tensor product of the first term appearing in the tensor product as the three-dimensional complex space, but the other term appearing as the tensor product is the three-dimensional complex space being raised to the tensor product of n plus m. And this comes into play in the fact that we have a product for K, and we also have a product over J, and we have a 3 by 3 diagonal matrix instead of a 2 by 2 diagonal matrix, and we have a product that's hitting this product of diagonal matrices with that's dependent upon two spectral parameters, namely u minus v sub k, as well as u prime minus v sub j prime, and we have I of a and j of b. So this is very much demonstrating how actually to define the quantum monodromy matrix in 3 dimensions, you just introduce some type of modification to the pre-image and the image space because they have to be the same of this mapping. Also related to the fact that the tensor product of the n plus m term comes into play because you have to look at contributions from each infinite degree of freedom that you're taking from the spectral parameters, which are indexed in K and J, with which range over big N plus big M terms. And the limit of the three-dimensional quantum monodromy matrix is given by the fact that we can write it in this, of the quantum monodromy matrix and also the three-dimensional transfer matrix, in which we can write of this form, in which we're taking two limits. The limit as big M tends to positive infinity, and also the limit as big N tends to positive infinity, and we're taking the product over J and I. And each one of the terms, because we're varying I and J at the same time, they're going to be dependent upon each one of these parameters, which is going to capture the lower order terms of the three-dimensional representation for the transfer and quantum monodromy matrices that we've been describing from several different perspectives throughout the series. And so the limit from the previous slide is related to studying the asymptotic properties of the two limits below it. Namely, we're looking at the asymptotic property of just the product over I and letting big N go to positive infinity of 1 sub I, 1 sub I, 2 sub I, all the way up to 9 sub I. Or we will also have to study the limit as big N tends to positive infinity from a product over J for 1J all up to 9J. And then taking these limits together simultaneously amounts to studying a double product of this 3 by 3 dimensional representation, and it's given by 1 sub I sub j at the same time all the way up to 9 of I sub j. And the expression of lower order terms in the weak infinite volume limit expansion for I and j terms, it's given by the fact that we can take some product, say from i's between 1 and 3, or some product from j is equal to 1 and 3, and we have to modify different types of terms in the 3 by 3 dimensional representation, such as the q of d sub j sub I term, which appears in the first entry at the top for the limit as big N tends to positive infinity. But on the other hand, if we're looking to take the limit as m tends to positive infinity, we're holding the I parameter, which appears in the first entry as a matrix, as some constant number, because we've already taken some product of terms in 1 degree of freedom, and we're trying to study the higher order terms of the approximation by taking products in another infinite or another degree of freedom that we want to tend to infinity in the infinite weak volume limit. So the outcomes of this approach that we have been mentioning is that we introduce all objects are manipulated in the three-dimensional QISM approach, and we discuss how specific terms in lower and higher order approximations of three-dimensional transfer matrices arise, and we establish comparisons with staggering and spectral parameters for the two-dimensional six-vertex model in previous works under domain wall, flat, or slope boundary conditions. And this is to say that this discussion can also have further connections because other assumptions can be imposed on the six-vertex model in this framework that relate to either colorizing or looking at the existence of an arbitrary number of colors by mapping to a three-dimensional Ashkin-Teller model. So the Ashkin-Teller model and the generalized random cluster model, they're originally models that I gained interest in from the logarithmic delocalization paper, in which you can look to perform a mapping of one model into another under a very specific assumption of parameters that appear in the Ashkin-Teller model involving hyperbolic signs and exponentials in 2 dimensions of coupling constants, which appear in a Potts model because the Ashkin-Teller model is ultimately coupling the two POTS models together. So that's another type of connection that can even be of interest, which can demonstrate an additional arena or additional area from another model that could see these types of arguments be applied to. And thanks for watching.